Okay, right. So don't worry, guys. We're nearing the end. Part 5. What we're going to look at now is a little bit more mathematical. We're not going to delve too much into the detailed maths. For that, you'll need to the papers. But we're going to ask questions on actual identifiability. So rather than just building algorithms, what can we say about completely independent of algorithms? What can we learn from data in these sort of self-supervised scenarios? And the first thing I want to stress is that there are actually two distinct mathematical problems that although they seem quite coupled, are actually quite independent. So first of all, we can talk about signal recovery. This is something that's been studied heavily in ideas like compressed sensing and generalized compressed sensing. The idea is if I'm given a signal model, which we're going to represent here as a probability distribution, P of X, is there a unique X for Y given A of X? So for a given probability distribution, P of X, and a given A, when is signal recovery possible? When is that mapping essentially one-to-one? And then there's the model, so that's the signal recovery. And then there's the model identification problem. If I am just given a set of measurements, so let's assume that I have the measurement distribution P of Y, which is just the measurement distribution induced by the measurement operator A applied to X drawn from P of X. When can I uniquely identify the distribution P of X from P of Y? And again, we're always really thinking about scenarios typically where A is an incomplete operator, so we're projecting down. Now, interestingly, all pairs of answers to these questions are possible. That is, there are settings where we can construct problems where signal recovery is possible, but model identification is not. We can construct situations where model identification is possible, but signal recovery is not. Similarly, both can be impossible or both can be possible. So although these things look quite connected, they are, to a certain extent, independent of each other. As I said, signal recovery itself has been studied extensively in compressed sensing. Usually, certainly traditionally, was focusing on the k-sparse model. So the idea was that the probability distribution P of X had a support that was k-sparse, or at least was approximated by a k-sparse support. And we'll see that sort of these ideas recurring in this part. Okay, so as I said, classical compressed sensing argues that if the support of P of X is low dimensional, or typically k-sparse, but can be generalized to other low dimensional settings, then we can expect this mapping under appropriate circumstances to be one-to-one. And we'll talk a bit about what we mean by appropriate circumstances. So we're basically going to be using this in part of the identifiability results to say, if I make the same assumption, so note that making an assumption that my set is low dimensional isn't the same as saying I know what the set is. So the set could be an arbitrary, if I just say it has dimension k, but I don't know what the set looks like, can I recover the set k? So I am injecting additional prior information, but it's kind of weak prior information. And I should also say that there's multiple ways of measuring what low dimensional means. Now, here we're getting slightly technical, and this is really a mechanism that is useful for actually going through the proofs, but is worth stating. This is something that comes from the notions of fractal dimension. So we define what's called a box counting dimension. The box counting dimension can be defined for compact sets. And essentially, what we do is you take your compact set, you see how many epsilon balls you can cover it with, you need to cover it with of size epsilon. You then let epsilon go to 0, and you look at the scaling of that, and that defines dimension. So this happens to be a a quite exotic definition of dimension. But if you think about it carefully, if you think about a two-dimensional plane and putting rectangular boxes covering it, how many rectangular boxes do you need of length epsilon? This scales to give you a dimension 2. Similarly, if you're in 3 dimensions, a dimension 3, etc. So it matches our common understanding of dimension in simple settings. So, for example, if you had a k-sparse set or a union of subspaces, if they're k-dimensional subspaces, and you take a compact set of that, then that would have box counting dimension of k. Similarly, if you've got a compact k-dimensional manifold, it would again have box counting dimension k. What it does mean is that you can actually have exotic sets. Julián was just talking about scale invariance, where maybe you've got some sort of fractal structure in that setting. Then this box counting dimension potentially generalizes to more exotic sets. But let's not worry about that for now. Okay, so we're going to start out by thinking about the signal recovery problem. And actually, we're going to make use of a theorem that comes from the dynamical systems community back in the early 90s from Tim Sauer and co-authors. And he showed that if my signal belongs to a signal set capital X that lives in some finite dimensional ambient space and its box counting dimension is k, then it can be uniquely recovered, i.e. there is a one-to-one mapping from the measurements y given ax for almost every a in the set of matrices from Rn to Rm, if under the condition that m has to be greater than twice the box counting dimension. If any of you are familiar with differential topology, this is very similar to Whitney's embedding theorem for embedding k-dimensional manifolds in ambient spaces. Well, roughly speaking, what we're talking about, or what we're aiming to get for recovery, is that if I live in R3, say here, and my signal set of interest is one-dimensional, or in this case, this one here, and I have 2 distinct points on it, what I want is, after I apply my measurement operator, that the points associated with these, so I'm not now directly observing the 2 different cats, but the points associated in my measurement space with the 2 different cats in my image space are distinct. So that's what we really look for. It's just a classic one-to-one mapping. So that is signal recovery, and it's nice to see that basically, and I mentioned this at the start in terms of computational imaging, if we believe that our sets are low dimensional, our signal sets are low dimensional, then we can expect to be able to get away with having fewer measurements of actual unknowns and still be able to recover our signal set. This is distinct from the notion of model identification. Interestingly, model identification itself is also a linear inverse problem, albeit in infinite dimensions. We can see this from a simple marginalization concept. So I can always write down the probability distribution for my measurements y as the marginalization of the joint probability distribution, which I can factor as the conditional probability of y given x and the probability distribution for x. So obviously this is just an expectation and therefore is a linear operator, and I can just write it in these terms like this. So in principle, I can also evaluate the model identification problem as a linear inverse problem and asking whether that linear inverse problem is recoverable, albeit I'm now in a more challenging setting in infinite dimensions. And we have to be careful here. Everything we're talking about is very much geometric. So we are talking about identifying probability distributions from other probability distributions. In practice, of course, from a machine learning point of view, we will have finite observations. And this really goes back to the question Marcelo asked Julián about what do you do when you have, why are some of these problems harder than they might appear in a sort of a nice platonic world? And that's because we don't really have access to to P of y here, we only have access to some approximation of P of y, which is based on the samples that we have. Okay. And I should stress this is really a statistical question, and the statistical questions of model identifiability are pretty much open. So I think there's some really interesting areas of research to be done there. Okay, so let's take this framework where we're going to assume that we have the perfect probability distributions and ask, can we learn with noise? And the answer is yes. We'll see. So in the noisy setting, we have y equals x plus some noise. Let's assume that it's Gaussian to keep it simple. So we're going to have just additive Gaussian noise. The conditional probability distribution is going to be a Gaussian, and our linear operator in infinite dimensions is just a convolution of the probability distribution on x with a Gaussian function, which is a deconvolution problem. Now, deconvolution problems, and you see this quite often in the literature, yes, they are strictly invertible, but if you've ever tried to deblur an image using, say, a Wiener filter, you will know that in practice, there's the difference between theory and practice. In practice, these things do not work. So we are working very much in an idealized setting. But we can think about this in terms of the Fourier transform of this setting. So we take the characteristic function of everything. So the characteristic function of y is equal to the characteristic function of x multiplied by the Fourier transform of the Gaussian kernel. And given that the Gaussian kernel is invertible, i.e. it's nowhere zero, then in principle we can identify P of x given P of y. Again, one could argue that we are in infinite dimensions, and so one might ask about the continuity of this operator, and it is not good. So this sort of again lends to the fact that these are very optimistic, idealistic results. In theory, we can also do look at Poisson, but that's slightly harder. Okay, so let's just think about what's happening intuitively. Intuitively, we're saying, again, let's go back to our, we're working in R3. We're going to assume our signal model is the main diagonal, so it's a one-dimensional signal model. I'm going to add some noise to it. So now my observed distribution in Y is going to be this tube. And so that tube, because the characteristic function, because the Gaussian kernel in Fourier is nowhere zero, can allow us to uniquely identify the original signal set. So that's roughly what we're saying. Okay, so that's the noisy case. What we're much more interested in, and what is much more challenging, is the incomplete measurement case. In the incomplete measurement case setting, remember we've got two ways to view this. We can either think about this either in terms of multi-operators or in terms of our concept of equivariance. So now we're going to ask the question, when can we uniquely identify P of x given y of x when the A's are incomplete? And we are going to make the assumption, rather like in the recovery problem, that P of x has a low-dimensional support. And that's important because once we have our low-dimensional support, then recovery means that we can actually ditch the probability distributions and just think about the support of P of x and the support of P of y, and ask when can we recover the support of one from the other. Again, before I state any specific theorem, let's look at some geometric intuition for this. Remember that we said with a single operator, we cannot do this in practice. We know that because of the null space. So again, let's work in R3, our signal set, but we don't know what our signal set is, but we know that it's one dimension. So we have a one-dimensional signal set. I'm going to observe it through the first two coordinates. So I see my signal set looks one-dimensional, which is good. In R2, in my Y set. But now if I try and think about recovery, The inverse, applying the inverse, obviously A is not one-to-one, one-to-one mappings, so it's the inverse of A is going to be one-to-many, and so we basically have to consider the null space. So anything that lives within this red subspace is a valid signal model. So I can put any squiggly line in there I want, and that's exactly what we said previously, that I can do whatever I want in the null space, and it still validates the measurement consistency. So in that sense, a single incomplete operator, I know I can't learn. But let's think about what happens now when I introduce multiple operators. Now I'm going to introduce multiple operators through the equivariant model. So but remember they're kind of equivalent to doing multi-operators where I just define my multi-operators. So again, I'm going to define my inverse operator, so my two-dimensional operator, but I'm now going to include a shift symmetry. So here's my original operator, and there's my null space. I don't know where I'm going to live in that null space, but now I can think about applying the inverse operator where I've got a shift T1 where I basically do a right-click shift on my coordinates, and the null space now lives in a different part of the image set. So my null space is now lying diagonally. I can do this again, and I get yet again another null space. So here I'm seeing that I have 3 different null spaces, and if I take the intersection of those, I can uniquely get back to my original signal set. So that is the intuition for what we can expect to do when we have multiple operators or we have a rich enough invariance model with respect to some group operation. Okay, so what does that actually map to in practice? That allows us to make a statement that is similar to the signal recovery statement but now for identifiability with multiple operators. So we're going to assume that we have multiple incomplete operators. So A1 to AG. They are mapping from Rn to Rm. So we're going down in dimension. But we're going to assume they're generic in the sense that I'm sort of randomly plucking them from the set of matrices from Rn to Rm. Now, in that setting, and again, interestingly, using the same mathematical tools that Tim Sauer and co-authors used for the signal recovery problem, we can show an identifiability result. And that basically states that if I believe that my signal set is k-dimensional, so if I know my k-dimensional my signal set x is k-dimensional, so I then have g different observation sets. So yg is just the mapping of the set xg into my measurement domain. Then, given these sets, I can uniquely identify the original set capital X under the following conditions. So I need that all my operators. This is true for almost every set of operators. So I'm drawing each of these operators from Rm plus n. When I say almost every, what I'm essentially saying is that the set of operators for which this does not work is measure 0. We're basically doing a Lebesgue measure 0 set doesn't work. So we know that it doesn't work for all operators, clearly. I can just choose 0 for all of them. But for almost every set of operators, it does, under the condition that m is greater than k plus n over g. So we saw, again, this sort of number occurring when we did the self-supervised learning. This basically tells us that the size of the group we need has to be, it depends on how many of these different operators we have and the dimension of the image space. Okay, so if we choose if we have access to a lot of operators, so in MRI we have access to a lot of different subsamplings, then we can essentially choose G to be large enough to kill this term here, and we get roughly that m is going to be greater than k. So actually, this is better than potentially the signal recovery case. We can recover even when we have a small number of measurements. An important thing to say, and this is true about the signal recovery as it is about the identifiability, and one can argue is a weakness of this form of analysis, is that, yes, we've said this is true for almost every result. So there's an awful lot of settings where this is true. And in fact, there's a very small set of settings where it's not true. However, this says nothing about specific settings. So I cannot actually, potentially one could say something about MRI operators, but introducing maybe something random. This is essentially a random result, and therefore you cannot say anything on a specific set of operators. Does this set of operators validate this problem? We can't say that. Okay. So what about a single operator? So again, we are going to assume that we have a single A now, and there's going to be a group operator. It's going to give us our virtual measurements. Again, we're going to assume that A is generic. But it's important to note, so the setting is G, we're going to take as a cyclic group. We would like to be able to take it to be a richer group. We haven't been able to do that. So again, that's kind of an open problem at the moment. But if G is a cyclic group, and we're identifying a k-dimensional G invariant set X is possible by almost every A in Rm by n. Notice that I have actually much fewer degrees of freedom here. In terms of the proof mechanism, we need degrees of freedom, and now that I only have one A to play with because all the other virtual operators are fixed by my group operator. But it turns out that we can still say something if m is greater than 2k, not 1k, 2k plus the maximum of the multiplicity of the representation. This is technicalities for representation theorem. We just need to think about it for the cyclic group. This is greater than 2k plus n over g plus 1. So let me just draw a comparison between this and the multi-operator case. In the multi-operator case, this 2k was k. So the equivariant setting is harder. We shouldn't be surprised by that. And there's also this additional 1 here, which it turns out if you look at the paper on this, seems to be necessary. So that we can't get rid of that. However, again, we can argue that if we're in the setting that if we choose a rich enough group, so we want, ideally this tells us that we want big groups. Small groups are not very useful to us, which is interesting because if you look at a lot of the early work on equivariant neural networks in machine learning, they were doing things like 90-degree rotations. So, which is great. You've got an additional set of rotations to augment your data with, but your group is pretty small, and so you're not really getting the full power. And certainly we found that doing full rotations, albeit an approximation, is much more powerful. So if we can choose a G to be big enough, then we can typically kill this term. And again, identifiability comes in line very closely to signal recovery, which is our ultimate goal. Again, finally, just reiterate my last point. This is in almost every result, so I am not making any statement about any specific operator, and that is a challenge for me. Okay, maybe I'm being too pessimistic. Maybe I don't need this low dimensionality result. Maybe I could just do it anyway. Maybe the theory's there to say that we could just learn any model. Well, the answer is no, but let's just see why that is. Okay, so we can analyze this quite nicely. Again, remember, model identifiability is a linear inverse problem, and we can analyze this through the characteristic function. So if I take any finite group of operators, then I can think about observing, instead of thinking about observing P of x, I can think about observing phi of x, the characteristic function. And I observe the phi of x, but only in the range of the projection. So a dagger A, the projection of the measurements back into the image domain. So I'm essentially can think about this as measuring on that set. I can accurately measure in the noiseless case the characteristic function of x, but elsewhere I can't. Now we know that there is a famous theorem by Kramer and Wald that any distribution x of p can be uniquely determined by all its one-dimensional projections. Okay, so I know that I don't need m measurements; I need one measurement. However, the key thing is the all. So what that says is if I'm in my frequency space, I do a one-dimensional observation. I see a line in frequency space. I can observe that. If I now observe that for all possible lines, so I basically rotate that line around the space, then I do truly observe the full distribution. But of course, we only have a finite number of operators in practice, and so in practice, it's not. We can't verify Kramer-Wald theorem because we would need an infinite number of operators. So I should argue people have argued that in the classic machine learning way, we can just assume that n being large is the same as n being infinite, and therefore, possibly if I had a very, very large number of operators, then I could use this to infer. But ultimately, if you've got a finite restricted number of measurement operators, or even more critically, a restricted number because of the group operator, then you can't make reference to the Kramer-Wald theorem. So to do this, so I've just said this already, but to do this, we would need G to essentially be. Yes.
Sorry. So that's to uniquely identify P.
Yeah.
Do we know if we don't really want P? We want the traditional estimator of x given y.
Yes, but to have that, you need to know what P is. If you can always estimate x from y, in every instance for y drawn from P of y, then you need to find P of x.
Okay, so they are equivalent.
Yes.
It's not that this one is harder than the other.
No, they are equivalent.
There are some nuances.
I think you can be able to reconstruct some obscure statistics of P of x given y without having the field.
Yeah, but that's if you so an interesting question is if you wanted so here we're talking about one-to-oneness and uniqueness of identifiability. Let's suppose that you don't have exact recovery, so we're in the noisy setting, and maybe you want to have the posterior mean.
Yeah.
That's an interesting open question as to what measurements you need or what setting you need to verify being able to reconstruct the posterior mean from P of y and the conditional model. But you don't necessarily need the whole of P of x for that setting.
And the other question is, obviously, linear inverse problems have been extensively studied by a range of communities. The mathematical inverse problems community has studied this from different forms of regularization. So other than the low dimensionality assumptions, are you aware of other forms of regularization that could help you recover at least parts of P of x when they're stable?
I guess if you're you can play different games. So you can put low dimensionality onto the set of distributions that you believe your distributions come from. So there's a compressive learning plays this game where you basically say the distribution I want to learn is not itself low dimensional, so the signals don't come from a low dimensional distribution. But clearly, if my distribution comes from a family of 1 point, then learning is trivial. If it comes from a line, so a one-dimensional set of distributions, then again, learning is much simpler. But whether that, I think for the particular problem we're looking at, because we're interested in both signal recovery and identifiability, the low-dimensional setting, the low-dimensional model on the signal set is, in my view, the right one.
That's the environment that support environment formations.
Okay, that's the end of that one. And so we've got one final part, which Julian's going to present to wrap up.